read the learning goals. It says I can use function notation to represent and evaluate a function. I can find the domain and range of a function as well as graph using transformations. And I can use the vertical line test to determine whether y is a function of x. So again, just mixed pre-calculus review. All right, so number 1 says evaluating a function. If f of x equals x squared plus x, evaluate the following. So I'm just going to be using substitution here. The first thing I'm substituting into the numerator is just what f of x is. So we know that f of x is x squared plus x. Okay. Minus, then I'm going to sub in f of 2. I'm going to just do a little side note over here. How would I find f of 2? What would I do to find that? I want f of 2. Yeah, I'm just going to plug in 2 into this f of x equation. So that's going to look like 2 squared plus 2. See how everywhere there was an x, now everything there was 2? So that would give me an f of 2 value of 6, right? So when I want to sub something in for f of 2, I'm going to substitute in 6 over x minus 2. Any questions about how I input those values? Okay. All right, so I really don't need the parentheses here. This is really just x squared plus x minus 6 over x minus 2. I'm going to try to simplify this as much as possible. What would you do to try to simplify that? Great, so we're going to factor the numerator. And so we'll factor it into x minus 2 and x plus 3 over x minus 2. We're factoring to see if there's a factor in the numerator that will cancel with the factor x minus 2 in the denominator. I'm going to cancel this whole factor with that whole factor. Right? Divide those out to get 1, and then all that's left is x. All that's left then is x plus 3. Any questions about that? Good? Okay. Take it little chunks at a time. All right, number 2, we're going to talk about domain and range. It says the domain, x values, which can be used for a function, is always all real numbers. And again, all real numbers, the symbol for that is that capital R with the double line through it. And it says for a function, the domain is always all real numbers unless the function is rational, an even radical, or a trig function. What's another way that we can write all real numbers using interval notation? Great. Negative infinity to infinity is another way we can represent all real numbers. We can't really define what infinity is, so I cannot put the inclusive bracket. I have to just put the parentheses. So again, the domain's always all real numbers unless the function is rational, an even radical, or a trig function. If the function is rational, then I want you to write denominator cannot be 0. I'll call this rule number 1. What this means is if I've got a rational function like 1 over x, what would be the problem with the value in the denominator being 0? Can't divide by 0, right? You would get undefined. I don't want an expression that's undefined. So when I'm talking about a rational function or a function with a fraction, I want to make sure that that bottom number or that bottom expression does not give me a value of 0. Okay. So in this example, right here, I would have to say that my domain would be from negative infinity to 0, union 0 to infinity. See how I'm including all of the values except 0? I did not put a bracket on 0, I put a parenthesis, which means everything up to, but not including 0. Okay, that's just an example of a rational function. All right, the second problem we run into is if the function is an even radical. If the function is an even radical, like square root, you cannot have a negative value under the radical. So what this means is, if example 2, let's say we had this function square root of x. What would be the problem with x being negative? If I had the square root of negative 2. That would be an imaginary solution, right? I don't want that. So when I'm defining my domain, I would not want any negative numbers. We'd have to go from 0 on up, right? 0 in the positive number system. Same thing with a 4th root or a 6th root. Any even root, you don't want negative numbers underneath the radical. Okay? And for number 3, says if the function is a trig function, then I want you to write tan x, cotangent of x, secant of x, and cosecant of x for all of those functions, tangent, cotangent, secant, and cosecant. We need to watch for vertical asymptotes. I'm abbreviating vertical asymptotes to be VA, but that's what it means. You have to be careful of vertical asymptotes. For example, if I'm looking at the tangent function, I know that when I graph the tangent function, we have these asymptotes here, right? And they continue on in both directions. What's the issue with asymptotes? Are you going to have a point on those asymptotes? No, it's going to be undefined there. So when you're defining what the domain is or what x values you can use, you cannot use the x values along those vertical asymptotes because it's going to give you an undefined value for y. Okay? So we have to be careful with the domain there. It says the range of a function is the set of y values that result from using the domain that is stated. So in these examples, we're going to find the domain for each of the following. In part A, why is there a red flag there that we're going to have a domain restriction? What do I see? I see an even root, right? It's a problem because we have a square root here. So this expression underneath the square root, we know cannot be a negative value because then I cannot take a square root of a negative value. So in other words, this x minus 2, whatever that value represents, is going to either have to be equal to 0 or greater than 0. Okay? Whatever x minus 2 represents has to be a positive value or 0. Okay? So if I solve this, if I add 2 to both sides, that means that x has to be greater than or equal to 2. Because if x was less than 2, like if x was 1, I would get 1 minus 2, which would give me a negative number under that even root. And I don't want to deal with that. Okay? So now let's write our domain in interval notation. X is greater than or equal to 2. I'm going to have from 2 to infinity. Why did I put a bracket around 2? You know, it includes that x value, right? It's greater than or equal to 2. If it was strictly greater than, I would have just put a parenthesis. But because it's greater than or equal to, that's why it's a bracket. All right, let's look at B. Does B meet any of those credentials? Is B a rational function? Do you see a fraction? No. Is B an even radical? No. Is B a trig function? No. So is there going to be any problems with the domain? Do I have to do any restrictions? No. So if there's no restrictions and it's all real numbers, you can just write that from negative infinity to infinity. Okay. Part C, what's the issue there? Got a fraction where there's a variable in the denominator. Right? Got a variable in the denominator. This is a rational function. Right? What do I not want to see show up in the denominator? 0. I don't want to have to divide by 0. So whatever this value x plus 3 represents, I know that that value cannot give me 0. Right? Because if it gives me 0, then we have a problem. It's undefined. So now let's solve for x. If I subtract 3 from both sides, I get that x can't be equal to negative 3. Okay? That's my only restriction. X can be anything else, it just cannot be negative 3. Right? Because if I plugged in negative 3 here, what would I get? Negative 3 plus 3, divided by 0. No good. So writing this in interval notation, I'll have negative infinity to negative 3, union, negative 3 to infinity. That's all of the points except for negative 3. Include all those negative values up to but not including negative 3, and then all of the values greater than negative 3. All right, part D, what's the issue here? What do you think? Danny, what's the issue here?
Trig function.
Trig function, okay? And not only is it a trig function, but it's one of the ones we listed, right? Tan x was the first trig function that we listed. Let's just think about what the trig function looks like. So if I'm going to graph the tangent function, I know I have an asymptote here at negative pi over 2, and an asymptote here at positive pi over 2. And I've got to graph this shape in between there, right? What's the period of one cycle of the tangent function? Pi, right? To get from negative pi over 2 to pi over 2, that's pi units. So if I add on another pi unit, what would be my next asymptote? What is pi over 2 plus 2 pi over 2? 3 pi over 2, right? And here if I subtract pi from negative pi over 2, what's my next asymptote? Negative 3 pi over 2, etc., right? This goes on infinitely in both directions, this shape, right? So I need to tell what my domain is. I cannot include the x values where I have those asymptotes, because it's going to be undefined at those vertical asymptotes. So the domain's kind of tricky to write, because it extends infinitely in both directions. This is how I'm going to do it. I'm going to put dot, dot, dot. I'm going to go from negative 3 pi over 2 to negative pi over 2. Then I'm going to union that with negative pi over 2 to positive pi over 2. Then I'm going to union that with positive pi over 2, positive 3 pi over 2, and then again I have dot, dot, dot from there. Right? It's going to go on forever like that. Okay, we're including all of the x values except for where there's asymptote. I'm not including negative pi over 2. I'm not including the x value pi over 2. Better. Any questions about that? Is that okay? Like I said, it's a little bit weird just because it extends differently in both directions. That's why we put the dot, dot, dot. Okay, so now that we've talked a little bit about domain, we're going to focus on piecewise functions. Who remembers piecewise functions from last year? A couple people. Have you at least heard of a piecewise function? Okay. So a piecewise function says functions have only one output for any given input. Evaluate each of the following. So I've got this piecewise function f of x. I'm going to be referring to the top part as equation 1 and the bottom part as equation 2. Really, it's the same within the same function, okay, but I'm just using that 1 and 2 so we can talk about it easier. Okay, if you're looking at equation 1, it tells you that x has to be strictly less than 1. And if you're looking at equation 2, it says x has to be greater than or equal to 1. Okay, so we've got our split at 1. If I want to evaluate f of negative 3, which part of that function would I plug it into? 1 or 2? 1, because negative 3 is a number that's less than 1. Okay? So I plug it in, I get negative 2 times negative 3 plus 3. We get 6 plus 3, which gives me 9. What about f of 0? Would I plug that into option 1 or option 2? What do you think? Anna, what do you think? Is 0 less than 1 or greater than or equal to 1? Less than 1. So I'm going to plug it into option 1. Yep, plug that into option 1. F of 0 is going to be negative 2 times 0 plus 3. So I just end up with 3. Okay. For f of 1, what would I plug that into? Option 1 or option 2? Option 2. Good. Option 2 is where x is greater than or equal to 1. So since I'm plugging in 1, I'll have 1 plus 4, which gives me an output of 5. Okay. F of 3. What am I going to do for f of 3? Let's see. Dan, what would I do there?
Option dose.
Option dose. Yep, that's a number greater than or equal to 1. So f of 3, I'm going to get 3 plus 4, which is 7. Any questions about that? Okay. That's how we use a piecewise function. As far as transformations go, let's just talk through what these transformations would be. If I have x minus c inside the parentheses, what would that be? What would that be? Right. Yes. I'm going to say right c units. X plus c inside the parentheses. Allie, what would that be? Left. Good. Left c. I have plus d just hanging out back. It's outside of parentheses. Let's see. Mason, what would that be? Up d units. Okay. Logan, what would minus d be?
Down.
Down d. Then I get to a negative outside of any parentheses. And so what would that be?
Reflection.
It would be a reflection. What kind of reflection?
Over the y-axis.
Opposite. Over the x-axis. Yeah, this is going to be a reflection over the x-axis, which is the same as what? Is a reflection over the x-axis the same as a vertical reflection or a horizontal reflection? I flip something over the x-axis. Is that a vertical reflection or horizontal reflection? Vertical, right? If I was going from opening up to opening down, that's vertically changing it. Okay, it's a vertical flip. Okay, so reflection over the x-axis, that's the same thing as a vertical reflection. You might make a note of that. The negative is inside the parentheses. That's also going to be a reflection, but this time it's going to be a reflection over the y-axis. Which if I'm flipping something over the y-axis, what kind of reflection is that? Horizontal reflection. Okay. And on the last one, you can see I have a negative outside the parentheses and a negative inside the parentheses, so both reflections are happening. This is a reflection over the x-axis and that's my hand sign, and the y-axis. Any questions? I feel okay? All right, so in these two examples, it says graph the following, state the domain and the range. So the first one, to graph it, I'm just going to reorder this a little bit. I'm going to make this negative x plus 2. So really, I'm just graphing a line. My y-intercept is 0, 2, and my slope is negative 1. I think that's the easiest way to graph that. So I'll make my y-intercept at 0, 2. And then from there, I'm going to go down 1 over 1, down 1 over 1. Okay. Now, if I'm talking domain and range here, is there any restrictions on your domain or what x values you could plug into that function? It's really not. It's a linear equation. Okay, there's no restrictions on the domain. It'll extend infinitely in both directions. So I'm just going to put negative infinity to infinity for the domain. And then remember, range is my y values. Are there any y values that I'm not going to use? If it extends infinitely up and infinitely down, really there's no restrictions on the y values either. Okay, so their y values will be all real numbers as well. Looking at the second example, we have radical x plus 2, right, the square root function. What does just the regular square root of x function look like? Show me the shape of it here. Right? It's kind of weird. It's like the, call it my wrapper function. You know? So we know what that looks like. It looks something like this, where we have a starting point at 0, 0, and it kind of comes up like that. Right? So what would x plus 2 do to the graph? What do you think x plus 2 would do to the graph? It's going to shift just to the left too, right? Anything that's tucked in there with the x and you're adding something on or taking something off, that's going to be your left-right shift. So this is actually going to shift my graph left 2 units. So I'm going to take that starting point, 0, 0, and shift it to the left. Now, if you want another point to plot, what could you do? Just pick an x value to plug in. What would be a good x value that you could plug in? Yeah. 1. Now, if you plug in 1, you're going to get 1 plus 2, which is 3. Square root of 3 is not super nice. What would be an x value, Courtney?
Negative 1.
Negative 1, sure. So if I plug in an x value of negative 1, I have negative 1 plus 2, which is 1. And the square root of 1, that's easy. That's just 1. So that would be a nice point if you want an extra point to know what it would go through. Okay? You could plug in 2 if you want, and get 2 plus 2, which is 4, and the square root of 4 would be 2, so it should go through 2, 2 as well. Okay, if you want a couple extra points. Or where else can you get points from? Second table, right, or graphic calculator. Right. But if you're doing it in your head, you can quickly just plug in some values for x. All right, domain and range. Let's talk domain and range here. Domain's my x values. Are there any x values we're not going to use? Look at your picture. Which x values am I not going to use? Anything less than, what's my x value here? Negative 2, 0. My x value is negative 2 here, right? I'm not going to use anything to the left of negative 2. So my x values at least have to be negative 2 or bigger. We can just tell that from the picture. If you like doing it algebraically better, you could write that x plus, you could write that whatever this x plus 2 is, under the square root has to be an expression greater than or equal to 0. Right? You could solve it algebraically as well by subtracting 2 from both sides. You know that x has to be bigger than or equal to negative 2. Okay, so whether you use the picture or use algebra, either way, we get that x at least has to be negative 2, and we can go up to infinity. Notice I'm making negative 2 inclusive with the bracket. There's no hole there. What about range? What about my y values? Looking at this graph, is there any y values I'm not going to use? What do you think? Danny, what do you think about the y values?
Can't go below 0.
Can't go below 0. If I look at the lowest point on this graph, the y value of my lowest point is 0. Okay? Is there any graph below that starting point? No. Okay, so my y values are going to start at 0 and go up to infinity. Any questions about that? Okay. All right, here's the last one. We've seen something like this before. This is not just a regular square root function because I've got x squared underneath that radical, not just x. Okay, so you have to be careful. This is actually derived from a circle. x squared plus y squared equals 16. Does everyone agree that's an equation of a circle? What would be the radius of this circle? If r squared is 16, what is just the radius? 4, right? The square root of 16 would be 4. So x squared plus y squared equals 16 is a radius, is a circle with a radius of 4. Now let's go ahead and solve for y and see what happens. If I subtract x squared on both sides, I get that y squared equals 16 minus x squared. And if I square root those sides now, I would get that y equals plus or minus the square root of 16 minus x squared. This is an equation of a circle. Now, do I have the plus and minus parts? No, I only have the positive form of that square root. So is it going to give you a whole circle? No, it's just going to be the top half of your circle, right? So part of your circle with the positive y values. But we know the radius of our circle. The radius is 4. So I'm going to make a point at 4, 0, 0, 4, and negative 4, 0. See how this would give me a radius equal to 4, right? And here's the top part of my circle. That should be more rounded, if you get the idea. Okay, that's what my graph looks like. Again, if you're not sure what your graph would look like, what can you do? Put it into your calculator. Great. If I wanted to graph this in my graphing calculator, I'm going to go into y equals. Okay. I'm going to put the square root of 16 minus x squared into my calculator. And you can see that I get that top half of the circle. Why would it look more like an ellipse in your calculator, Caleb? The window. Notice how this is a rectangular screen. The screen's not a square it's not a square, right? So since this is 10 by 10, going up 10 units here on this axis is going to be more squished than doing the 10 by 10 window on this axis, right? So it'll look more like it's pulled horizontally, stretched outward, just because your calculator is not a square. Okay, your calculator has a rectangular window. Okay, so if you're going from negative 10 to 10 and negative 10 to 10, it's going to look more like an ellipse on your calculator. Okay. If you want to pull exact points, you can go into your table, second graph or second table. You can see here is my point negative 4, 0, and there's errors beyond that. Here is my point 0, 4. And then here's my point 4, 0, and there's errors beyond that. Okay. So, good way to do that. All right, let's go ahead and talk domain and range. So again, domain's my x values. What x values do I use here? What do you think?
Negative 4 to 4.
Negative 4 to 4. And I'm going to put in brackets because it includes both of those x values. Right, there's nothing over here, and there's nothing over here. If I look at this point, it's negative 4 to 0, and this point is 4 to 0. Right, so if I'm looking at my x values, they go from negative 4 to 4. What about my range or my y values? What would those be? Kara, what would you say for your range? What's the lowest point here? The lowest point is either 4, 0 or negative 4, 0. So you're right, the y values at the lowest point are 0. And this looks like it's my highest point. What's the y value at my highest point? 4. It's going to go from 0 to 4, inclusive. Any questions about that? All right, vertical line test. It says if any vertical line touches a graph at more than one point on the graph, then y is not a function of x. So the vertical line test can be used to determine if something's a function. Here's the most basic examples I can think of. All right, here's your x squared graph. We all know that's a function, right? We've heard teachers say it before that it's a function. Graph's a function, y equals x squared. Now, if I take this line and I move this vertical line, is there anywhere that the vertical line touches a graph at more than 1 point? No, right? That's why it's a function. Now, if I draw a different graph, I draw one that looks like this, and I take that vertical line, is there anywhere where that vertical line crosses the graph at more than 1 point? See how it's crossing the graph at 2 points? That is not a function, okay? For each x value that you pick, you only want one y output in order for it to be a function, okay? For this x value, see how there's 2 y values, okay? That makes it not a function. For each x value, there should only be one y value.
Okay, so for the vertical line test, it says if any vertical line touches a graph at more than 1 point on the graph, then y is not a function of x. In these examples, we're going to determine whether y is a function of x. Let's look at example 1. First thing I want to do is just get y by itself so that it's in a calculator-friendly format so I can type it in my calculator if I need to. So I'll subtract x squared from both sides. We get negative y equals negative x squared plus 15. Divide both sides by negative 1. So we'll end up with y equals positive x squared minus 15. Now if I were to graph this, I'd have a y-intercept down here at 0, negative 15, and it's going to be a U-shaped graph. Okay, now that one is going to be a function, because anywhere I would draw a vertical line, it would only cross the graph in one spot. Again, if I draw a vertical line over here, it only crosses the graph in one spot. So because for each x value, there's only one output value or y value, this would be a function. Yes, function. Okay, let's do the same thing for example 2. I'm going to subtract x squared from both sides. So we'll end up with y squared equals negative x squared plus 25. And I'll square root both sides. We get y equals plus or minus the square root of negative x squared plus 25. You can even rewrite this to say plus or minus the square root of 25 minus x squared if you like that better. And I had to think about what this shape is. Before I even rearranged it, I could tell that this is an equation of a circle. Okay, so it would be a circle with what radius length? A circle with a radius length of 5. And instantly I could see that where I draw a vertical line, it's going to be crossing that circle in more than one spot. So I already know that that's not a function. If you don't recognize that it's a circle right off the bat, you have to get into calculator-friendly form. So that's why we get into y equals form. And now that it's in y equals form, I can type it into my calculator. In my y1, I would put the positive form of the root. And in y2, I would put the negative form of the root. Okay. The positive form of the root is going to give me the top half of that circle. And the negative form of the root would give me the bottom half of the circle, which altogether is going to end up giving me the entire circle. Okay. So a circle is a relation. A circle is not a function because for a given x value, there's more than one y output.
Okay. Number 3, we have this crazy thing. How am I going to determine if that's a function? Solve it for y. Get it into a calculator-friendly form so you'd be able to graph it on your calculator and use the vertical line test. Okay? So the idea is I want y equals. So I'm going to collect these terms that have a y in them, and I'm going to keep them on the same side as the equal sign. So let's go ahead and move the x squared over. I'm going to add x squared to both sides. Okay, like that. Now, if both of those terms share a y, what could I do so that I only see y once? Factor out y. Very good. Factor out a DCF of y. If I factor out y from the first term, all I'd be left with is x squared. If I factor out y from the second term, all I'm left with is 6. And then how would I get y by itself? Divide both sides. Divide both sides by this factor x squared plus 6. Or that binomial x squared plus 6. That gives me y by itself. I get y equals x squared over x squared plus 6. Right, so let's just use the calculator to see what this looks like. When you're typing it into your calculator, you want to make sure that you're doing x squared divided by, and then putting this x squared plus 6 in parentheses. Why is it imperative that you put x squared plus 6 in parentheses? How is that different than this? How are those two things different?
The bottom line, you could have added 6 to the whole thing, like x squared over x squared.
Great. So on the bottom one, we would have done this step first, using order of operations, and then added 6 to whatever that quantity was. Whereas in the top one, I'm actually doing this part first, doing the addition first, and then the division. So you want to make sure order of operations are what they're supposed to be. You should not put it in your calculator this way. You want to make sure you're using parentheses. So let's see what that looks like. All right, y equals, we've got x squared divided by x squared plus 6. Right, that's what it was, right? Thanks. So it looks like this. It's kind of weird. If you want to see what it looks like a little bit more closely, you can always zoom. You hit the zoom button, and you want to zoom in maybe on the point 0, 0. Looks something like that. Now, if you were going to draw a vertical line, so that cat says, please return to Miss B. Anywhere that vertical line is it going to pass more than one point? No, it's just crossing one point. So is this a function? Yes. Okay, so that last answer would be yes. Okay, any questions? All right.